Welcome to this video. In this video, I will be discussing regarding Lorentz transformations and some applications of special theory of relativity. So one of the important points that separates special theory of relativity or speed that are close to velocity of light with the normal classical regime is that in classical sense, when the velocities are much smaller than speed of light, time is an absolute parameter. It is same in all the frames, but in case of this, when velocity is comparable to speed of light, the notion of time becomes a frame dependent quantity. So these are the transformations between position and time of different frames. So here the deltas means that these are essentially differences of coordinates, because what is a particular coordinate, the coordinate of a particular object depends on the choice of the origin. So essentially what makes sense is to discuss the differences of the coordinates rather than any absolute coordinate. And so if we consider two frames, S prime and S prime is moving with a velocity v with respect to s, and then when velocity is much smaller than light, or in general notion, we can say that this x prime plus v times t, that is just the x coordinate that is observed in the frame S, and the t equal to t prime because time is absolute. This is something that you can say is associated with common sense. These are just the Galilean transformation. And but what is actually true is that the frame, the coordinate differences in S and time differences are related to the frame S prime in this particular fashion. So and the gamma factor, as we all know, is the factor of 1 over under root 1 minus v square over c square, and it is greater than or equal to 1. And so this delta t prime that is here, it is important to understand that we have to specify what this means. So delta t prime is the time differences of events. This is a time difference of events that occur in S prime, but it is measured in S. So it means it is the clock. The clock is in B, but it is seen by A. So there is only one observer. The observer is in A, and he is measuring in B. So with this understanding, let us just try to apply it to a few of case by case. So the first part where we apply it is time dilation and length contraction. So the notion of time dilation is that there is a clock that is fixed in the frame of B that is moving with a velocity v with respect to a ground frame G. Suppose this is a train and it has a clock in its ceiling, and if the train has a window and A is observing from that window to see the clock, what is the time comparison that A can do with the clock in B and his own clock? That is the main point. So we will use this Lorentz transformation to see the comparison. So as the clock is fixed, delta x B, which is essentially delta x prime in our formula here, that is equal to 0, and I want to relate delta t A with delta t prime, that delta t prime is delta t B, that is time seen in B's clock as seen by A. So there is only one observer and he is in ground, and they are related by a factor of gamma, because here you will essentially put x prime, that is delta of B, 0. So here we use this point. So and what we say is that, well, the clock of A, when A measure his own time, it is fast as compared to when A sees the B's time. So with this we now understand the notion of this length contraction. Here what we do is that we perform a measurement on this moving frame to measure its length. Initially, suppose we have this party Bob, and he takes a L length rod, sits in a train, and the train starts moving with a velocity v. Now what A does is that at a same instant he just records the two ends of the rod when it passes by two of the points. So suppose at a particular instant he records the point where this end intersects. This is suppose x1, and this end intersects. This is x2, and then x1 minus x2 must be the length that A must observe for the rod. So the essential point here is that the time the measurement of this rod's length, it is made simultaneously in A's frame. So delta TA is 0. Delta x prime, which is the length of the rod in B's frame, is just L, because B just took this L length rod and was traveling with a velocity v. And now we have to find delta x, which is just delta xa. So the way to find it is that we use again the Lorentz transformations, but with the frames we have to understand which frame we need, because now what we are given is time difference in A frame and the length in this frame of B. So let's see. So here what we will do is we will just say that, well, what is the Lorentz transformation if I am observing A from B? So these are the transformations when I am observing B from A. So if I have to observe A from B, I will just superpose a velocity of minus v. So essentially what that Lorentz transformation will amount to is just a change of sign of v going to minus v. So with that change in sign, what we have is delta xa is related to delta xb by a factor of gamma. So essentially what we say is that length gets contracted because gamma is greater than 1. So the length measured by A will be less than L. So now we will try to look at both time dilation and length contraction together. So suppose consider we have a train. The train has two clocks separated by a distance L, and now the point is these two clocks are synchronized in the train. That means if an observer is in the train, he sees that the two clocks are ticking together, and now the question that we ask is that what is the time that A observes in these two clocks that is moving in B? So we have to find time in B as observed by A. So the point is A measures these two times together. I mean, it's like A opens his eyes and together he notes these two time because he want to compare the time in B what he sees. So delta TA is 0. Delta xb is the length of separation in the train of the clocks, and delta xa is the length between the clocks that A measures. So A measures a contracted length, so it is L by gamma. So with these 3 points we have to just find delta t in B frame. So delta t in B frame, which is the moving frame, is related to the rest frame by a minus sign, and this is what we get. Now we will just put the values, and the answer we get is that minus LV over C square. Now first let's try to understand this result. This result says that, well, because the length is contracted, and like if this is origin, this is plus L, so equivalently this delta t is actually the time difference of clock C2 and C1 in this particular order that I am showing here. So what this means is that C1 is ahead of C2 as seen by A. So because C1 is reading more time than C2. So when C2 is suppose at 00, which is suppose 12 o'clock, then C1 is reading a time that is greater than 0 by a factor of LV over C square. So what this means is that the clock at this rear end, it is running at a faster pace than the clock in the front in the frame of B as observed by A. So what this means is that if suppose there are two people and they have agreed to sing together in B, but their singing, even if the singing started together in B, as observed by someone in B, the singing will begin together. But for a person who is observing in A, the singing will not begin together. The singing by a person standing below C1 would have begun before the singing by the person at C2. Assuming that they both have agreed to sing at 00, when 00 occurs in C1, C2 will be lagging behind. So 00 would not have occurred in C2. So now we, with this understanding, we look at one more problem. This is the problem of bombing a train. So what happens is that suppose we have a train that is moving with a velocity v, and there is a platform, and in the platform there are two bombs separated by a distance of L in the platform, and let us call one of the bomb B1 and another one B2. So the bombs are set up by Alice, suppose, and what will happen is that the bomb are they are in synchronization such that the moment the two bombs reaches the time 00 or suppose 12 o'clock, the bombs, they have a timer attached to them. Whenever they both reach 12 o'clock, they blast together. So when they blast, they will leave some mark on this train, and the question is, what is the distance between the marks? So let's try to address this question, that what is the distance between the mark left by these two bombs on the train. So let's try to see what Alice says, who is the bomber. She says is that, well, in my frame the bombs, they blast together, so delta TA is 0. In my frame the length of separation is L. I need to find the length of separation in this moving frame, but from this length contraction, I know whenever the length in the moving frame is related to my frame by a factor of 1 by gamma, so it must be gamma times the length that I am seeing in my frame. So this is a simple length contraction argument given by A. Well, and it looks quite valid. But now, what does Bob say, who is not the bomber, but obviously he knows that there is this synchronization and bomb, they are blasting together problem. So Bob says, well, in my frame the platform is moving along with the bombs to the left side, and if the separation between the bombs is L, and this is a moving frame, what I will observe is L by gamma, because my frame is at rest. So in my frame the bombs, the mark will be at a difference of L by gamma. Now you see, here we have a contradiction or a paradox. Essentially the point is that this mark that it leaves on the train, the bombs that they leave on the train, can be verified, because the train can be made to stop and the mark can be verified where the two bombs blasted on the train, and the answer cannot be both of them. So one of the answer is correct and one of the answer is wrong. And the point is that argument made by Bob is incorrect. The reason being that while discussing this length contraction argument, we made a very important point, is that measurement of the length is made simultaneously at the frame whose length is getting contracted. So here indeed this is true that the bombs that are there, they will be separated by a length L by gamma. But that is a different fact. What we need is that when the two bombs have exploded, and the point is the bombs in the frame of B doesn't explode together, but in the frame of A, who was Alice sitting here, the bombs explode together. So that's why it is essential to understand the observer's point of view. So what is the correct argument made by Bob? We will see that. Well, now Bob corrects himself. He says that, well, indeed, the bombs are separated by a distance L by gamma as per me, that means in my frame, in P frame, but they have not yet blasted. That's my point. When Bob looks at A's clock, so the essential point is there are two clocks here that the bombs are associated with. When Bob is in rest in his own frame, when Bob looks at A's clock, that means the clocks are attached to the bombs, because the frame in which the bombs are is moving with a velocity v, the clock that is in the rear end here, it will show a time that is more than the clock that is in the front. So basically, when time equal to 0 has reached in the rear part, the front bomb is still lagging by a time of LV over c square, as we saw in the previous argument. So what this means is that when Bob looks at A's clock, the bomb B1 will, or the bomb in the front, will need VL over c square more time in A as seen by Bob for the blast after the second bomb, that is the bomb in the rear end, has blasted. So this means the time difference, the time of the second blast as measured by Bob, will be gamma times VL over c square, because this only VL over c square is the time that Bob sees on the frame A, but he needs to find his own time, so there will be a factor of gamma multiplied. So here we are making use of time dilation. And so now Bob says, okay, after this much time, the second bomb will be blasted, and in this much time, the train would have traveled this much distance, multiplying just by a velocity v. Then the total distance between the first blast and the second blast is the initial distance that was between the bombs plus this distance that is coming due to this time dilation, or this fact that the two events are not simultaneous. And then the total sum of the distance is gamma times L again. And hence the point is, the mark will be made at a distance of gamma L. So A and B, they both agree on where the mark will be made by the bomb blast on the train. And they can both measure and verify that once the train stops. So that's all for this video. In this video, I discussed this problem of this time dilation and length contraction. That's